given an array with 500 elements, we need to find an element in this array that is neither the minimum nor the maximum. Not the minimum, not the maximum. That's the only requirement. Okay? Can we say that we can always use fewer than 8 comparisons to find this element? This I treat as a little tricky question in this quiz. So I like to give you a hint a little bit. Okay? Yeah. Yeah. Think about 500 elements. The goal, use fewer than 8 comparisons to find just one element that is not the minimum. You're sure it is not the minimum, and it is not the maximum. A little tricky. Yeah. Yeah. Here, I like to give you point to the direction, right direction to find the solution. Okay, yeah. So this is the first question. In this class, you can see a little tricky. Later, we will have many questions like this one. Yeah. So the first one, I'd like to give you some idea. Okay. For questions like this, one commonly used method. Remember last time I talked about reduce the problem size, right? A common way to find a solution, reduce the problem size. Here, the problem size, 500 elements, 500. That number is pretty big. If I make this number smaller, do you think it's easier? I make this number smaller. Can you, along this direction, reduce this number and find a solution? Think about that. So that is one step towards the solution. All right. Second, another step. Here, I reduce the size. I make this size smaller. Okay, yeah. I change this number to 498. Just 2 fewer elements, 498. And I solve the same problem. Do you think I can do a little better? I reduce the problem size by 2 elements. Then I need to find one of the elements that is not a maximum, not a minimum. Okay, yeah, all right. Use certain number of comparisons. Here, we do not know how many, just certain number of comparisons. Suppose we can find certain number of comparisons, all right? Yeah, okay, suppose we can find, let's say little a number of comparisons we can find, okay? I reduce to 498 elements. If I can solve the problem with 8 comparisons, can we say we can also solve the original problem, 500 elements, with 8 comparisons? If I can solve one with fewer elements, 498, with 8 comparisons, can you also say we can solve the original problem with 8 comparisons? Think about this question. It's a critical step. Think about this question, critical step. Can we say that? we reduce by 2 elements. Then we just use A comparisons to find a solution. Can we go back to the original 500 elements? We can use no more than A comparisons to find a solution. Is it true? Is it true? Let me give you another step. Let's just take 498 elements from the original 500 elements. We find a solution. Is that a solution also the one can also we treat as one of the original solution? We just, when we start from the 500 elements. We take 498 for subset from it. Then we find a solution with 8 comparisons. Can we go back to the original question and we say, we just use this one as the original solution? How about that? Is that okay? Think about that. We take a subset, find a solution. Then we treat this solution as the original solution. Is that method working? Can you connect? Anyone? Or you have a question?
Does it matter if they're like distinct elements?
Yeah,
If they're the same?
distinct elements.
Wait, so all these are distinct elements?
All distinct.
Okay, so that makes it huge.
Yeah, all distinct. All right. Yeah. All distinct. See? All right. Think about that idea. Take a subset, find a solution. Can we treat this one as the original solution? Yeah, so you feel okay. All right. Yeah. If distinct, you feel okay, right? Okay. Yeah. If you feel okay, can we reduce? Why we just reduce to 498? Can we reduce to 100 elements and do the same thing? 100 also okay, right? We take 100, find the one, neither maximum nor minimum, with a solution, with a comparison, 8, A, B, C, D, 8 comparisons, A comparison, A, B, C, D, 8. Can we treat this the same solution as the original one, 500? If we can reduce to 100, can we reduce to 10 elements? If element is this the smaller the size, the better, the fewer comparison we need to find a solution. If we can reduce 10, can you reduce even more along that direction to find a solution? Okay, along this direction to go. All right? See how far you can go along this direction. How far you can go. When you reach the end, when you push to the end, you get the best solution. Push to the end, you get the best solution. How about this idea? Yeah. You figure it out. I do not tell you, right? You figure it out. Okay? Yeah. That's the thinking. Yeah. So learn how to think in this class, thinking in this way. Okay? Logic reasoning, do analysis like this. Change the problem size. Manipulate the problem size. Okay. All right, so let's start our notes today. All right. Part C, asymptotic notations. This topic, very abstract. This part is the most abstract part in this class. But we have to learn this topic. For this algorithm, this is a big, important topic in this class. But we will not do too much abstract concepts. But the concepts in this part, after we learn it, we will use it from now on, all the time. All right, C.1, Introduction to Asymptotic Notations. Let's recall limits of two growth functions. We did a calculation last time, limits. We use L'Hopital's rule. So then some students may worry a little bit. Yes, I got a question from a student yesterday. The question is, because some students, they feel they almost forgot the details of calculus, calculating limits. For this class, I give you several examples, show you how to calculate the limits. But my requirement is you only need to understand how to derive certain important results using the limit way. In my assignment, I will not assign you limit calculation questions directly. Okay, directly. So do not worry too much. But definitely, if you understand the limit techniques, it helps a lot to understand the logical reasoning part of many of our results. All right, so when we consider limits of two growth functions, so we take the ratio, right? The ratio like this, f of n over g of n. And try to find the limit when n goes to infinity. The first question is, how many cases do we have when we look at the answer of this limit? How many possibilities we could have? First, I want to list all the possibilities. Okay, all right. Here, I can think of these four possibilities. The first one, zero. Okay, so that's we can see frequently, many examples, we get this zero limit. First possibility. Second one, constant c, but this constant c not equal to zero, okay? Non-zero constant. Non-zero constant, the second case. The third case, infinity. Infinity, third case. The last case, other than the first three cases, we have one special case. The limit does not exist. The limit does not exist. It's also possible, right? Limit does not exist. It's different from the above three cases. Limit does not exist. Can you imagine this situation? The limit does not exist. Ratio of two functions. When n approaches to infinity, the limit does not exist. Yeah. Think about that. All right. Let me give you a simple example. Oh. All right. Let's consider this case. Let's consider the ratio of this limit. Does this limit exist? Does this limit exist? This f of n over g of n. Yeah. Let's plug in numbers. Yeah. When n equals 1, 1 over 4, right? When n equals 2, 3 over 2. Then back to all the function, so all the number, even number. So this pattern repeated alternatively. Okay. Yeah. In this pattern. Okay. Yeah. When n is an odd number, 1/4. When n is an even number, 3 seconds. This pattern. Okay. With this sequence, can you say its limit exists or not? No limit, right? Yeah. Limit, you have to converge to one number, then you can say its limit exists, right? Converge to one number. Here, no convergence, right? Up and down, up and down. No convergence. No convergence, no limit. Okay? Yeah. No limit. So that's our case number 4. No limit. Okay? Yeah. All right. Then in our discussion, so we want to talk about all these 4 cases. Okay, all right. Case 1. Case 1, because we need to compare which growth function grows faster in case 1. Can you see which function f of n or g of n, which one grows faster? If their limit, the ratio of their limit equals 0, g increases faster or f increases faster. Function value, faster means function value larger. Function value larger. When n is very large, G increases faster, right? Yeah, because the ratio is 0, f of n smaller than g of n when n is very large. Yeah. So in this case, we use this terminology to represent their relationship. Order of growth of f of n less than order of growth of g of n. Here we introduce this concept, order of growth. There is a growth order. Growth order. What's the growth order? Yeah. So later, I will give you some, closer explanation. Here, some abstract concept, order of growth. A function grows in certain order. There is order. Some measure. We want to measure its growth rate, how fast it grows. So we need a number to measure it. So we use this order of growth. What's that order of growth? Later, I'll talk about that. After I finish these 4 cases, then I talk about the order of growth. All right, that's the first case. So we can compare the order of growth. After we see the limit, we can say something about the order of growth. All right. Case two, the ratio constant C, non-zero constant C, although non-zero, but in our case, positive. Because our growth function is always positive. Okay. Our growth functions come from counting number of basic operations, right? Counting number of basic operations. That's our growth function. So that number should always be positive. Positive. Yeah. All right. So for the case number 2, we say they have same order of growth. Although non-zero constant, that C could be large, could be small, but remember, when we take a ratio, we cancel out that constant C. When we take a ratio f of 2n over f of n, we cancel out that constant C. Here, also, g of 2n over g of n. We compare these 2 ratios. The constant C is gone. Okay? Yeah. The constant C is gone. Yeah. All right. So we treat case 2, same order of growth. Okay? Yeah. Case 3, order of growth of f of n is greater than order of growth of g of n. Yeah. This time, f function grows faster, increases faster. Infinity, yeah, f of n dominates g of n. Okay? So it should have higher growth order. All right, yeah. Case number 4, unknown. Right? Case number 4, the limit does not exist. That means we cannot say anything at this point. We need to do some more work. For case number 2, we need to do some more work to get the answer. Okay, yep, all right. Yeah, but for these cases in our future discussion, we want to use some compact notations to represent all these cases. Compact notations. we do not want to write a lot of words. Okay, yeah. So we want to use some special abstract notations to represent the same meaning here. The first three cases, because case number 4, we cannot say anything. So for the first three cases, we need to use some compact notations to represent these meanings. Yeah. All right, so let me show you the first compact notation. F of n, in this case, we just write f of n belongs to little o of g of n. Little o notation here. We use a special notation we call the little o notation. What's the meaning of little o? When you see this little o, you just immediately connect the ratio of their limit equals 0. That's the meaning of little o. Okay? Yeah. Little o notation. That's the meaning. If you take the ratio and the limit goes, where n goes to infinity, it must be 0. Then you can write this little o notation. The reason, yeah, because this abstract notation, we don't need to write a lot of words. We know its meaning. Yeah, that's what we need. Yeah. We do abstract here. We do abstraction to make our representation as simple as possible. That's the goal. This is our first asymptotic notation. First asymptotic notation, little o notation. Okay, yeah. So you know the limit, the meaning behind it, and order of growth meaning behind it when you see this little o notation. Okay, all right, so that's the first one. Second one, big theta notation. Big theta, capital theta, big theta, right? Not little theta, capital theta, big theta. Big theta notation here, you know, the limit, the ratio. Yeah. So here, actually, if you see the big theta notation, yeah, it's different from little o. Little o notation, you can connect to the limit directly. For this big theta notation, you can say they have the same order of growth. But for the limit, if the limit equals the constant c, if the limit equals constant c, sometimes it equals constant c, sometimes not. Sometimes yes, sometimes no. Why is that? Yeah, later I come back to answer this question. Why sometimes the limit is constant c? Sometimes like this, no limit. No limit. So later I will explain this question. Yeah. Okay, all right. The third case, this time you say f of n belongs to little omega of g of n. Little omega, our third asymptotic notation. Little omega. The ratio is infinity, little omega. Okay? Yeah. Third asymptotic notation. Yeah. Yeah. And you can use the limit directly. Case 1 and case 3, you can use the limit directly. But case 2, you should be careful when you use the limit. Yeah. Because there is another situation, the limit does not exist. But you have this big theta notation. Yeah, so yeah, later I will explain this case. Yeah. All right. So here now you can see here from our discussion at this point, you can already see the limit way has some limitation, right? Limit. We have some limitation. Yeah. Because for case two, sometimes the limit does not exist, but we have case two. How can you get that? How can you get that? We still have case two, but the limit does not exist. Think about that. The limit does not exist. That means it's the case four, right? Case four. For case four, there is a possibility. For case four, there is a possibility f of n belongs to big theta of g of n. That's quite complex. So we need more discussion for this part. Or we need to find a way different from the limit way, another way. Here, you can see the limit way has limitation. So we need to find another way to answer this question. All right, so let me show you our second method. We need a new method for case two. Using upper bounds and the lower bounds. When limit does not exist, we can consider the upper bounds and the lower bounds of the function to describe, to compare their order of growth. Yeah. Another method, objective. Yeah. So when the limit of the ratio does not exist, but we can still compare their growth functions. How to compare? Using inequalities. How to compare? Yeah. So our method, second method, use the inequalities. Okay. Yeah. Two inequalities. Lower bound, one inequality. Upper bound, another inequality. Two inequalities. Okay. All right. How to do it? Yeah. All right. So here, usually, yeah, because when we compare two growth functions, usually that g function we like to take simple functions like power function. Yeah, here, this is the power function, all right? The power function, n to the kth power, okay? Power function. Then, because log n commonly appears in the growth function, it's quite common. We see log function. So here you can see the second one. Basically, it's a power function times log function. A power function times log function. Okay? Yeah. So the commonly used G function type. Yeah. Because G, we want to use simple functions to do comparisons. Power function. Yeah. All right. It's very rare. There is another case, more complicated, but it's rare, very rare. So that is log, another log, nested log function. Nested log function. Yeah. It's very rare. Yeah. In this class, we won't see it. Yeah. We won't see it. Okay. Log of another level log function. Nested log function. Yeah. That could happen. Yeah. But fortunately, in this class, we do not need to. We won't have any algorithm in this class. Okay. All right. All right. All right. So the function f of n could be a complex function, more complicated. Yeah. Yeah. So here you can see, basically, we use a simple function, g function, to describe complicated function, f function. That's our goal. We want to do this kind of comparison. All right. And use some constant multiples of g to approximate f function. Constant multiple to approximate f function. That's our objective. Okay? Yeah. All right. Specifically, can we find two positive constants C1 and C2 such that C2 multiple of f of n or g of n, yeah, less than equal to f of n and less than or equal to C1 multiple of g of n. So here you can see lower bound. This is the lower bound, right? C2 multiple of g function as the lower bound of f of n. C1 multiple g function, we use it as the upper bound of f function. If we can get this kind of inequalities, then we can say, f of n belongs to capital theta, big theta of g of n. Okay? Yeah. Even if the limit does not exist. No. Here we do not use the limit. We use inequalities. We do not use the limit. We do not use the limit. Okay? Yeah. So that's one thing. That's one thing. Another thing I like to talk about, remember in a previous slide, I mentioned that order of growth concept. Order of growth concept. Okay? Yeah. Here you can see what's that order of growth concept. That concept. Okay? All right. Yeah. Look at the power function. Yeah, here. First, the power function. Here. Why we use power function? Yeah. Power function, the good thing is when we talk about order of growth, then the answer is simple. So for n to the kth, this is a power function, then the order of growth is k. Just its exponent directly. Okay? K, exponent directly. We can treat that as order of growth, k. Yeah. Then you can do comparison. The k is larger, the order of growth is larger. When k is smaller, the order of growth is smaller. Pretty straightforward. Yeah. Here you can see the number k. All right, yeah. But for this log function, there it's hard. What is the order of growth of log function? It's hard. It's hard. Okay, yeah. So it's close to 0, but not 0. Okay, so order of growth close to 0, but not 0. Order of growth of that log function. Okay, yeah. So later I will give you some special method to handle this log order of growth for the log function. Yeah, there is some complexity here. But I delay it. I delay it when we work on some homework questions. Then I talk about the order of growth of log function. There, okay. I will assign you some questions related to log function. At that time, I talk about order of growth of log function. All right. Yeah. C.2, define asymptotic notation. This time, I need to give you the rigorous definition, formal definition of asymptotic notations. So a little abstract, but after our preparation, the first two slides, it should not be that hard. It should not be that hard to understand. Formal definition of some of the asymptotic notations. First, let's look at a big O notation. Big O, not little o. This time, big O. Big O notation. So what's that? The formal definition. For a given function g of n, the notation big O of g of n represents the set of functions, set. Okay? This notation represents a set of functions. You know the set concept. A set of functions, f of n, that satisfy the following condition. Following condition. So what's the condition? There exists some positive constant c, and some non-negative integer n0, such that this inequality holds f of n less than or equal to c times g of n for all n greater or equal to n0. That's the formal definition of big O notation. Here you can see, in this case, we only have the upper bound. Constant multiple of g for f function. We only have upper bound. We don't have the lower bound. Only upper bound. In this case, we call it big O notation. Second, there is this n0 here. What is the role of this n0? You understand the c constant. Yeah, we need some c constant. But you may not understand why we need this n0 here. Yeah. There is some importance related to n0. Some importance. We need it. We need it. N0. Okay? Yeah. N0, first you can see N0 is another constant, right? It's a constant. N0 is also a constant. But this constant is a little different. Yeah. Because when you choose this constant, N0 constant, you have freedom to choose N0 constant. Okay? So you have freedom to choose larger N0, smaller N0. You have some freedom to choose. But after you choose it, you must fix it. After you choose it, then when you grow that n variable, n is variable, okay? This n is a variable. It's not a constant variable. Yeah. It changes in a discrete way. We call discrete variable, right? 1, 2, 3, 4, 5 discrete variable. Okay? You take the discrete values, but it's a variable. So when you change the n values you never change this N0, okay? Because it's a constant. After you select it, you have to fix it. Yeah, so that's the details. Then for this definition, all right, after select, you must be fixed, And here, there is another terminology we use to describe this N0, its role, Sometimes people do not say N0, People do not say N0 directly. Sometimes people say, when N is sufficiently large, use this vague description. This is a vague description. When N is sufficiently large. Because you may ask, what do you mean sufficiently large, right? You may ask. Because it's quite subjective, right? For different people, the meaning of sufficiently large could be different. For you, 1 million, it's enough, sufficient enough. But for another person, 10 is sufficiently large. So it's subjective. It's not objective. All right? It's subjective, not objective. But after you learn this formal definition, if people ask you what's the exact meaning of sufficient, you just go back to that N0. Because you need to choose appropriate N0 constant. But you need to find it first. Okay? You need to find that N0 first. After you find it, now you have the definition of sufficiently large. When N is greater or equal to this number, we treat as sufficiently large. When N is less than this number, we treat not sufficiently large. That's the exact meaning. But this N0 depends on the particular problem, right? For different problem, your N0 is different. So for the given problem, then you need to decide, you need to determine that N0 constant. Later in our examples, I will show you some different N0 constant. All right, then we need to understand visually this graph. The f function, we want to measure the order of growth of that f function. But here in this graph, you can see we use a constancy multiple of g function. That's the graph of this function. We can use it as an upper bound of f function, but there is one special condition. N0, this vertical line, N0 line, it's important. The upper bound condition only true after the n value pass this vertical line. Before this vertical line, it may not be true. So you can imagine, before this vertical line, the graph could be like that, all right? No upper bound anymore, before this vertical line, okay? All right, It is a little abstract, The first time, it may not be easy to understand. It is a little abstract, okay? Especially, for upper bound, you may feel fine. I feel some of you may have doubts on this part before that vertical line. Before that vertical line. So that part, that unknown part, we don't know the behavior of these two functions before this vertical bar. Let me delay another chapter. So Later, I will come back to explain this, this area, this unknown area. Okay? We need to do something. There is something we need to do in this shaded area. Okay? All right. Let's look at another asymptotic notation, big omega notation. After you understand big O notation, big omega notation, just the other side of the inequality. The previous one upper bound, this one lower bound. How about that? We change from upper bound to lower bound. Then we get this big omega notation. Okay? Yeah. The description pretty much the same. We change to this time big omega notation. Yeah. So then inequality, we change to lower bound. C constant multiple of G, we use it as the lower bound of f function. Then we call it this set of function, this whole set of function we call big omega of G of n. Yeah. And also this n0 sufficiently large, this constant n0. Yeah. And the graph similar to the previous one, but this time we use C constant multiple of G of n as the lower bound of f function. And there is some unknown part, right? Here is it doesn't matter. Yeah? It says it doesn't matter which one faster, which one slower, not important. Not important, doesn't matter. Yeah. But I will give you the story why it doesn't matter later. Why it doesn't matter. Okay? Yeah. You need to do something. Yeah. But this part doesn't matter. Yeah. All right. Yeah. So that's the big omega notation. Okay? Yeah. So you put it together with that big O notation. Yeah. Yeah. All right. Then the third one, our last one. Okay, third one, big theta. We learned big theta. We just come back, use this formal definition to describe it again. But you have big O, you have upper bound, you have lower bound. You put them together, you have big theta. You have both upper bound and lower bound. So the big theta notation, we just write a version with two constant C, C1, C2, and also N0 constant. Yeah. And this time we have both the lower bound and upper bound when n sufficiently large. And the graph is like this, upper bound, lower bound. Pretty straightforward. Yeah. That's all we need to learn in this class, asymptotic notations. Yeah. Here, for this part C, we have seen 6 different, right? 6 different. Little o, big O. Little omega, big omega. Big theta. 5, not 6. 5. We have learned 5 asymptotic notations. Yeah. But the most commonly used, only 2. All right. The 5 you may feel too many, right? Too many. Yeah. But most in our future discussion analysis, we use 2 of the asymptotic notations. Which 2? Big theta and a big O. Only these 2. Big theta and a big O. 2 commonly used asymptotic notations. Other, yeah, we rarely touch them, okay? Although we define them, but we rarely touch them. Yeah. So not too hard. Not too hard, only 2. Okay, yeah, yeah. All right. Any question at this point? Let's move to C.3, examples of asymptotic notations. This time I want to show you a few simple examples. Let's start with some simple examples first. Yeah, example, part 1. Next time I will give you a little harder examples. Today, there are 3 simple examples. Yeah. Next time, 4 harder examples. Example 1, show that n plus 2 belongs to big theta of n. Very simple, right? Very simple. All right. So I show you, how to solve this problem, this question. All right. Here you see big theta. So you know the meaning of big theta, right? Big theta. To answer a question like this, usually we have 2 different methods. 2 methods. Big theta, based on our understanding from parts C.1, C.2, 2 methods. The first one, limit method, limit. The big theta, we know if the limit is constant, f of n over g of n, if the limit is constant, then big theta. So it gives us limit method. So here we can calculate. N goes to infinity, n plus 2 over n. This limit, it's easy, right? Easy to find the answer, right? 1, right? It 1, not 2. All right, 1. I hope you can understand. I do not need to explain how to get a 1. Okay? Yeah. If you feel puzzled, you do division by n. In the numerator denominator, you do division by n. Let me write one more step. If you feel hard to see, division by n, both numerator denominator. So you have 1 plus 2 over n over 1. When n goes to infinity, this goes to 0. 2 over n approaches 0. So 1 plus 0 over 1, that's 1. Okay? Yeah. So if you want to calculate it, it's 1. 1 like this. Okay, all right. Yeah, but here, I want to show the second method. The second method, we use the formal definition. We need to find the upper bound, lower bound, and a constant n0 also. Constant n0. Okay, all right. First, let's start with n plus 2, this function. First, let's look at the lower bound. Which constant multiple of n we can use it as the lower bound? Constant multiple of n we can use as the lower bound, less than or equal to this. This n plus 2 constant multiple, as simple as possible. 1, yes, good. 1 greater than 1. You drop 2, smaller. All right, but how about the upper bound? A little harder. How about upper bound? Which constant multiple of n we can use as the upper bound of this function, n plus 2 function? Definitely n squared is the upper bound, but your upper bound is, because you change the order of growth. N squared, the order of growth is 2, but here order of growth is 1. You change the order of growth. That's not good. Okay? Yeah. All right. Yeah. Yeah. So here you have that C2, and you only need n greater or equal to 0. It's true. Yeah. But for the upper bound, can you replace 2 by n? Can you replace 2 by n to make it larger? Replace 2 by n to make it larger. If you can do that, do you need n greater or equal to 2? Because you need some condition to make this happen, right? If you need n greater, you get n0. Remember, you have freedom to choose n0. You just use that freedom right here. Now, you can determine that vertical bar, n0, that vertical bar. Okay? So here you choose 2, that n0, after this 2 line, yeah, this inequality is true, less than or equal to 2n. All right? Yep. So then we get constant 1. So here you can see constant C1, constant C2, constant n0. Yep. N0, both inequalities should hold, but you pick the larger one. So you pick n0 equals 2, not 0. Because you want both true, both inequality true. So when n greater or equal to 2, both true, both inequality true here. Okay? Yeah. So you get that n0. Yeah. So for the second method, you need to determine C1 constant, C2 constant, n0 constant. Then you prove it. You prove it. Method 1, you just find the limit. These 2 ways. Okay, yeah. That's the first example. Second example, show that n cubed belongs to big omega of n squared. Big omega we know lower bound. Yeah. Here. This one easy. Yeah. Because n cubed greater or equal to n squared when n greater or equal to 0. Yeah. So simple. Constant C equals 1, n0 equals 0. Yeah. That's it. Yeah, lower bound. Okay, like this. Yeah. By definition. This time, if you use limit is not good. Okay. So for this big omega notation, limit is not good. Okay. Try to avoid limit. Avoid the limit way. Okay. Avoid the limit way. Okay. Yeah. Not good. Yeah. All right. Yeah. The last example of today. Yeah. Sorry. Yeah. I have about 5 minutes. Let me finish it. Last example. This time, n plus 2 cube belongs to big theta of n cube. Yeah. Definitely, if we use the limit, it's quite straightforward. So you can do it easily. Yeah. Because we can take cube out of the limit. Then inside, we do not have the cube. It's 1. Then 1 cube is 1. Yeah. So for the limit way, it's simple. Yeah. So I do not need to repeat it. Okay. I only want to explain the definition way. Lower bound, upper bound. Yeah. Yeah. Because we did a similar one before. Can we use the similar way, just to modify a little bit to answer this question? The lower bound Tell me, constant C multiple of n, what C should we use here? Same as before, right? Yeah, yeah. N cube. C is 1. So n cube. So lower bound, simple, and also greater or equal to 0. How about the upper bound this time? How about the upper bound? Similar way as we did before, but we need to modify slightly for the upper bound. Replace 2 by n. Yeah, we still replace 2 by n, right? Yeah. And so we get a 2n. After that, we raise to cube. Yeah. N0, n greater equal to 2. Then we calculate 2n cubed. So we get 8n cubed. 8n cubed. So another constant, 8. So C1 is 8. C1 is 8. Okay? Yeah. Do it in this way. Do it in this way. Yeah. All right. Yeah. Yeah. Here, let me use 2 minutes to explain. There is better way that many students did before. Better way. So what's that? Many students, when they see n plus 2 cubed, they expand it. They use some formula to expand it to get n cubed plus 6, right? 6n squared, right? 12n plus 8. They apply a plus b cube formula to expand it. But if you expand it, it becomes much harder. Don't do it in this way. You make your life harder in this way. Lower bound easy, right? Lower bound, you just drop these terms. But for upper bound, it's much harder to handle the last 3 terms. Last 3, how can you get they are less than or equal to 8n cubed? Not easy to get. So if you do not expand, very easy from here, you get less than or equal to 8n cubed, and you just use some appropriate n0 now. Don't expand, all right? Don't expand, yeah. Yeah, because sometimes I give the function with higher exponent. Yeah, I remember I assign a function raised to 5th power. Then expansion will be longer, and it will be harder to estimate upper bound. So don't do it in that way. Okay? All right. All right, that's it. So finish part C.